Very much, Dan. Thank you all for coming here. I wanted to say one thing which is not on the slide, which is I'm soon coming to Harvard. I'll be starting as a faculty member in the computer science department here, not too far from here in the Maxwell Dorkin building. And if you find some of the questions over here interesting and provoking, please come find me. There are a few other people like me in that building, and we're hoping to have stronger connections with people like you. So that said, let me start telling you about this low degree testing problem. So this is a talk that I prepared basically for math audiences, so it should be self-contained. If something is not making sense, please ask me. This is not physics, so there will not be statements that will be made without proofs, or these are, I will not make statements as theorems unless I have a proof somewhere. They may not be given in this talk, but they are all formal statements and formal proofs. Okay, but the first slide is a little bit of a stretch. So this is just a way to motivate the question, why study questions of this type? I want to say this is really a generic thing. Many years ago, Kepler, he was sitting around with all this data that he was collecting. Tycho Brahe was this Danish astronomer from 1550 to 1600. He was trying to figure out what was explaining all the planetary motion around the earth, okay, planetary motions. And the general picture that people had was here at the center of the universe is the earth. There's the moon which rotates around the earth, and then the sun which rotates around the moon, around the earth, and then all these other planets which are rotating around the sun. Okay, that was the picture, that was the belief, and they wanted to confirm this thing, and they were collecting data as where are the points at planets at various times of the various times, and how do we sort of confirm this particular hypothesis. Tycho was not able to confirm any hypothesis. He passed away in 1600, but in the meanwhile he actually spent 10% of the Danish GNP during this period. So that's pretty impressive, not during the entire period of his life, but during the period where he was invested in it. It was a fair amount of expense trying to figure this out. Johannes Kepler was an understudy to Tycho Brahe, started from 1575 and continued past this thing. He actually believed a different picture, which was actually more close to the truths, which was the earth is at the center and the planets are rotating, but in circular orbits, not in elliptical orbits as we understand now. And furthermore, there was a very precise statement that Kepler believed in, which was that the ratio of the radius of these different circles was not just arbitrary. The radius of a circle was determined by the radius of the inner circle, of the radius of the next inner planet, closer planet. And how was it related? Well, you put a platonic solid like a cube or an octahedron or some such thing. As you keep going out, you put a solid with more faces, and you put that solid so that it encloses the previous circle, previous sphere, and then put a sphere enclosing this orbit that gives you the next radius. This was the very precise claim that Kepler believed in, and unfortunately this very precise version of the claim turned out to be false, but Kepler was eventually able to prove it. He did this by apparently stealing Brahe's data. He took this data without permission. He worked on it for 9 years actually. I mean, you have the data in front of you, you think the most heavy part of the computation of this enterprise would be collecting the data, but analyzing the data was not trivial either. It took him 9 years to finally find out what was the truth. The truth was, he was able to confirm Copernicus. He discovered the laws of planetary motion along the way. He realized that this platonic solid idea doesn't really work, doesn't go anywhere, and he also fixed the circle into an ellipse. Okay, so this was all done. This is how Kepler came up with this profound theory. What's interesting to me, and this is just take this with a grain of salt, is why did it take 9 years to do this thing? I mean, this is what it takes to see if a data fits a low degree polynomial. Okay, so this is elliptical orbits. How long does it take to figure this out? Apparently a lot of time. Why does it take a lot of time? Well, one of the things in this case, I don't know what really happened, but very often when you are looking at large amounts of data and many variables and so on, if you want to ask the question, is this is there some simple explanation for it? it seems that there is no way to test this thing short of finding the simple explanation which does work. Okay. So, if you have a polynomial in 10 variables and you want to know if it is maybe of degree 5, some degree 5 polynomial in 10 variables which explains it, this immediately leads to 10 choose 5 possible coefficients that you have to find, which is a pretty large number. Okay. So, you are looking at around 1000 coefficients before and you have to find the values of these 1000 coefficients, then determine if the data fits this thing. Question is finding all these coefficients really necessary? That is the question that we really are going to be looking at in the rest of the talk, and we will try to give you an answer not in this setting, and the reason it will not be in this setting is over here we really want to think about real numbers and errors should be allowed, some small amount of tolerance should be allowed. I will be talking about this problem over finite fields. Okay. But other than that, but really this is the kind of question. I will be looking at data and looking at trying to answer the question, is this data really correspond to a low degree polynomial? What kinds of answers can we expect here? Okay. So, from now on I am going to give you precise definitions of problem statements and so on. The first slide was not really precise. So, we are going to be working with finite fields. That is the reason for this is just that this is the domain which I am more comfortable with, and this is where we were able to come up with very, very clean definitions of the problem. Their modern theory of computing should really try to push this kind of work to other settings, but it has not happened yet. So, we are going to be looking at the f sub q is going to denote a field of cardinality q. We are going to be given access to a function. We can query the value of the function at any point, n variate function over this field, and this function maps all of these n variables down to a single element of the field. What we would like to understand is this function really a degree d polynomial or not, and we will be happy, we will be tolerant with errors in a certain sense. What do we mean by tolerant? So, first thing that we want to do is we do not want to query the value of the function everywhere in order to answer this question. Okay. We want to be able to do some random sampling, look at the value of the function in some maybe carefully chosen points, but not deterministic points, and we want to make sure that we do not query the value of the function too often. Okay. And before I go there, I mean degree, by degree I just mean the usual degree. This is a formal definition, but I suspect we are all on the same page. We are looking at the total degree of any maximum degree of any monomial. Degree of a monomial of the form x squared y cubed is really 5. So, this should explain what degree means. What does essentially mean? Over here I have essentially. So, I will allow for sort of errors in a certain sense in the thing. If your function is a degree d polynomial, you must accept. Okay. You do not have a choice anything. No matter what set of values you looked at, your function is a degree d polynomial, you have no excuse to say I will reject this function. Okay. On the other hand, if your function is very close to a degree d polynomial, you get to say do whatever you want. If by changing the value of the function in 1% of the points, this is a function with a finite domain. Okay. There is only a finite number of input values. You can change 1% of this domain and you get a function which is a degree d polynomial, then I do not care whether you consider it a low degree polynomial or not, fine. But if you have to change more than 1% of the values, I would like you to reject this function with some probability at least a half, or I think maybe 2/3 or some such thing. Okay. Why? Because I'd really, if I have a function which was perfectly a degree d polynomial and then I change its value at one place, just one place, immediately its degree jumps from being d to something like n times q. Okay. So, goes from being something very small to the maximum possible. I would not like you to spend an inordinate amount of time trying to figure out that there was this one change. I really do not care. I am happy to say mostly this was a degree d polynomial and 1% you change its value in a few places, that is good enough for me. Okay. So, that is why we are happy to do this. What we are hoping is that you make very few queries into this function. You do not ask for the value of the function everywhere, very few places. Okay. Does this make sense? All right. So, degree, a formal notation that I will use all the time is the distance between two functions will be just the fraction of places where I have to change the value of the function f to get the function g. Okay, this is the distance between f and g. Does this make sense? So it is a finite functions on finite input, finite set input. So we will just measure things by the uniform distribution on the domain. All right. So there might be a few variations and some specific refinements later, but this is the broad class of questions that we would like to answer. So in this talk what I would like to tell you is why we study this kind of question, a little bit of motivation for why this thing, and even why over finite fields. It actually turns out it is not a question without applications. I will tell you a little at least I should be able to convey to you the results that are available, and hopefully the results themselves are surprising, and then depending on time and so on I might tell you a little bit about the proofs that are used to prove these things. Just a little bit of flavor of the proofs, just enough to convince you that yeah, it is not completely obvious the theorems, and some work needs to be done. Okay. All right. So why polynomials? So before talking about why test to see if a function is a polynomial, let us ask the question, why study polynomials at all? Why are they interesting? Turns out polynomials of low degree are a central concept in error correcting codes, and by virtue of that also very important to computer science. And one of the features, a very basic lemma about polynomials that is extremely important in the setting is this polynomial distance lemma. It goes by many names in many different cultures, but it is really an age old folklore kind of a statement. If you take two polynomials whose degree is at most d and they are distinct, f is not equal to g, then the fractional distance between them is noticeable. Okay. It's, if you are looking at the case where the degree is less than the field size, then the fraction of places where you have to change f to get g is at least 1 minus d over q. So think of a case of polynomials of degree half the field size, then you have to change its value in at least 50% of the points to go from 1 degree d polynomial to another. Okay. That is a big change has to be brought in to go from one polynomial to the other. Note this statement over here has no dependence on the number of variables. If there is any dependence on the number of variables, it is in the dimensionality of the problem, it is in the, please come in, it is in the dimensionality of the problem, how many coefficients are there, etc., but not in the distance bound. Okay. And these are the kinds of statements that will be very interesting to us, statements where we can talk about d and q and dependence on the two without having any dependence on n. These kinds of statements will be the ones that are most interesting to us. And just if you fix n equal to 1 univariate polynomial, what I am saying is the very obvious statement, two polynomials of degree d cannot agree on more than d places without being identical, or equivalently their difference, if it has more than d roots, then it is the 0 polynomial, right. So that is the statement, it generalizes completely cleanly to any number of variables. Okay. All right. Okay, so this is the distance lemma. It says that and by the way, there is a variation which says what happens when the degree is greater than the field size, then you get some noticeable distance between f and g. Also it's, you have to change it on some, if you fix q and d and you let n go off to infinity, the fractional distance between f and g still remains some constant. It depends on q and d, but it does not go to 0 as n goes to infinity. And the exact bound is actually this quantity, and it is well motivated, but maybe I will not describe it to you right now. Okay. So there is such a thing. One thing I will use is this notation delta sub dq, which is the minimum possible distance between two distinct polynomials of degree d over fq. Okay. This is a quantity that this is the quantity that we are claiming is at least some constant depending on q and d, roughly q to the minus d over q. So this feature, the fact that this distance is positive or even something pretty large, is very useful in error correcting codes. If you have some information that you want to encode, you want to preserve so that it is resilient to change, then you think of that information as the coefficients of some polynomial. You try to represent the information as the coefficients of a polynomial. You encode it by its evaluations everywhere, and the fact that there is this distance property over here tells you that if I change the value of this encoded representation, I do not immediately ruin the thing. You have the information out there to recover thing. If you look for which is the polynomial of degree d which is closest to the function at hand, then you can I am not telling you about the algorithmics how you can compute this coefficients, but there is a unique polynomial which will be close nearby, and so you can actually recover the information. The information is available. Okay. All right. So this is how polynomials are used in computer science and information theory. Before I go on to telling you why should we do low degree testing, let me define the problem of low degree testing a bit more formally. We will be talking of two parameters. In fact, really the only interesting parameter is the locality L. What is a low degree test? It will decide that it is going to look at, we have this huge domain fq to the n. I really most of the times I am thinking of n as going to infinity very, very fast. So it is a n dimensional space, the size of the domain is exponentially large in n, it is really, really, really large. What we would like to do is pick some L points in this domain, a set of queries q, and say look at all the restriction of the function f to this domain, this very local domain. Locality to me just means the size of the neighborhood, how large, how many points have I looked at the value of the function. So I am going to look at the function restricted to the set q, and I am saying going to accept some subset of these functions and I am going to reject others. Okay. The set of functions that are being accepted is this set denoted by capital S. Okay. So some things I will accept, others I will not, and I would like to, this is what a low degree test is. Somehow it picks a set of queries q, somehow it determines the set S, and once it is determined that, the test is fixed. It is going to say look, I am going to accept if my function restricted to this set q is a member of this family. Okay. That is what a low degree test is. Does it make sense? It is a very simple definition. What are the kinds of guarantees that we want? If the function that we are looking at has degree less than or equal to d, we must accept with probability 1. We had already said this. And what we would like is the following. This is slightly different than what I had earlier insisted on. What I had insisted on earlier was that you should reject things which are far with some constant probability. Now what I will say is slightly different. I would like to say for every function you must reject it with, there is a lower bound on the probability with which you must reject it. How much is that lower bound? It is some epsilon. Think of epsilon as some number between 0 and 1, 1/3 might be a reasonable number, a tenth is okay, some constant, some whatever you want to think about it, epsilon times the distance of this function from the space of degree d polynomials. Okay. If I must change the value of the function at 5% of the values to be able to get a degree d polynomial, then you must reject it with 0.5, and epsilon is 0.1, then I might just reject it with probability 0.5%. On the other hand, if this function only differs from degree d polynomials in one location, then I get to reject it with, I should reject it with probability q to the minus n times 1/10. Okay. So just proportional to the distance, the larger the distance, the higher the probability with which I reject, the smaller the distance, the lower the probability. Okay. That is what I would like, and this is what would be called an L epsilon low degree test. Okay. So the main object of focus over here is really L. What is the smallest L we can get away with? And particular, should L depend on n? Most of the answers will say L does not depend on n, and you can get away with pretty good values of epsilon which may not even depend on q and d and so on. All right. So there is a slightly more interesting view of these tests. What we have, this function is, the function f is a very global function. It is applying to this exponential, and its domain is exponentially large in n. Okay, huge, huge, huge input. By deciding to look at its value at the set q, I am having a very local view of what this function looks like. What we would ideally like is that this local view and this global view are very closely correlated. So if f happens to be a low degree polynomial on the local view, it should look like some low degree polynomial restricted to this set. If f is very far from being a low degree polynomial, on the local view, earlier we were insisting that it should not look like a low degree polynomial. Now we will be even more insistent, we will ask that on the local view you are actually far from any low degree polynomial. Okay. Even on the set you do not look like any low degree polynomial, I cannot change its value in one or two places and get a low degree polynomial. Even on this local view I should be very far. That relationship if we can get, we will say that the test is actually robust. There are two parameters and alpha is very closely related to that epsilon, L is the same. We will say the test is L alpha robust if for every function the expected distance of the function on the local view is at least alpha times the expected distance, the total global distance of the function. Okay. Does this make sense? So I am producing, the test tells me how to sample Q and S. Once I look at Q and S, I can say, you know, how far is f restricted to Q from functions in the set S. That is another quantity, this is a random variable, I can look at its expectation. This expectation I would like it to be related to the global distance. So this is really a local to global relationship that we are exploring. The big distance is the quantity of interest, the small distance is what you can measure with a few samples. It would be nice if there were theorems relating the big distance to the small distance. Okay. This is the kind of questions that we will be interested in. The two notions, just a local low degree test and a robust low degree test, are not very unrelated. The alpha, the parameter alpha which differed from that parameter epsilon is actually bounded by epsilon from both above and below, but bounded by a factor which depends on the locality of the test. So if you can prove that some test has a small locality and has alpha which is a constant, that is great because it actually tells you a lot about how good the locality of the test is in this measure, but it tells you even more, and those are the kinds of results we will be pursuing today. Okay. All right. So this is all the definitions, and if anybody wants to sort of has any questions about it, you should ask me about it. This is the definition that we will be looking at in the rest of the talk. Okay. Let me give you maybe a simple example. So the general goal, we want to make the size of the queries very small, we would like epsilon and alpha to be as large as possible, the larger they are the better they are. Okay. So before I give further motivation why did we start looking at this, and even there I will not be able to say much except to point you in a general direction, let me first give you a concrete example of what can you do. Let us start with a very simple case, d equal to 1. I think even d equal to 0 is not a completely trivial example. What is d equal to 0? What is the class of functions that we are looking at? Constant functions. Okay. Even when you are looking at constant functions, I mean, you know, if you look at sampling them for majority, is the majority of the function values 0 or the majority of the function values 1? This is a non-trivial task. I mean, the fact that you can query a constant fraction of the population in order to determine whether the majority of the function is 0 or majority of the function is 1 is a non-trivial statement. It is the sort of beginnings of statistics. But here we are asking more sophisticated questions. So now we are starting to ask questions where actually the structure of the domain matters. It's, you know, whether constant functions, it does not matter what is the domain, you can permute it any way you want, the things do not change, the property does not change. Now it will actually matter what input is what. Okay. So degree 1 polynomials are given by n plus 1 coefficients, right. There is a constant term C0 and then summation Ci xi, n plus 1 coefficients. So it is an n dimensional vector space of functions. This is the ideal set, these are the functions that you must accept. If I ever give you a degree 1 polynomial, a hyperplane or whatever you want to call it, you must accept. And this is a setting where the distance is very large. If you look at two linear functions and you ask how much of the domain can they agree on, well, they would agree on at most 1 minus 1 over q fraction of the domain. So even if you take the smallest q that you can think about, 2, there are finite fields of size 2, two linear functions, two affine functions will disagree on 50% of the values. Okay. So, this is to go from one affine functions to another, you have to change a lot. What kind of locality can we hope for? What is the epsilon, what is the alpha? Well, distinguishing between epsilon and alpha does not make much sense here, because as we will see, the locality we will strive for is a constant. So, you know, these will only alter things. The epsilon and alpha are only going to be off by constant factors. What is the smallest locality? And here is already the important point. You know, look, you know, you do not need to look at n values of the function in order to run this test. You do not need to look at square root of n or log n, no dependence on n at all. You can actually hope for L to be constant. You can look at the value of the function at a constant number of points and hope that something will work. What is a reasonable test? Well, okay, if q is greater than 2, then you can actually even get locality 3, and actually there are tests and we can examine them, but I will not describe that. Let us look at the case where which will work even if q equals 2. The test that I will describe will make 4 queries into the function. Locality is 4. What am I going to do? I am going to look at 4 values of the function, the value of the function at u, at v, at w, that should be a w, and then the value of the function at alpha u plus beta v plus gamma w, okay, where alpha, beta and gamma are just values from the field, okay, non-zero values from the field. So, I will pick u, v and w and look at the value of the function at these 4 places, and if it and alpha, beta and gamma non-zero, I will pick them at random. That is my test, and if this identity holds, I accept the function. If it does not, I reject the function. That is it. Okay. So, this is just 4 queries. The space, the dimensionality of the space was n plus 1, it was going to infinity as n went to infinity. The locality is a constant. It is clear that if my function is a polynomial of degree 1, if it is of this form, then this identity will hold, okay, with probability 1. For every u, v, w, alpha, beta, gamma, this identity will hold. The seminal result in this field, due to Blum, Luby and Rubenfeld, they started this line of work from 1990, shows that actually this test has constant epsilon. Epsilon that they were able to prove was something like 2/9, very strange number, but it was a constant independent of everything. Well, the only parameter over here that is really significant is n. You could work with large fields if you want, you could work with small fields if you want, does not really matter. You can actually get epsilon at least 2/9, and then in a later work where we started introducing discrete Fourier analysis to analyze questions of this form, and this is the starting point of Hostad's involvement with Fourier analysis in this field, we can actually prove that epsilon actually that you get is 1. So, this is almost the ideal relationship. So, the probability with which you reject a function is proportional, is just lower bounded by the distance, the fraction of points where you have to change the value of the function to get it to be a low degree polynomial. Okay. Epsilon equal to 1 is the best that you should really hope for. Why is that? If I take my function f to be completely random, okay, my function is a random function, then what is the probability that this identity would hold? Okay. Well, let us fix f of u, f of v, f of w. There is one value of f of blah 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 which will satisfy this identity. The probability that f would take that one value at that point is 1/q. So, a random function will be accepted with probability 1/q, it is rejected with probability at most 1 minus 1/q. A random function also happens to be 1 minus 1/q far from the set of linear functions. So, the best epsilon you can hope for is 1, and that is achieved by this test. Okay. Does this make sense? So, this is a fairly simple looking statement, but already the proof ingredients over here start to become fairly sophisticated. It stops taking a combinatorial view or even a simple algebraic view of these functions, but really starts to look at a more analytic view of these functions. So, you really start looking at elements in fq as vertices in q minus 1 dimensional space, functions which are mapping to this thing are now going to be looking, you are going to look at them as if they are function in q minus 1 dimensional real space, Euclidean space, and analyze them according to this way of looking at things, and that gives us the ability to analyze these things. Generalizing to higher dimensions, what degrees, what will we get? These are the kinds of questions that I'd like to be able to explain in this talk. I'll mostly give you answers to these kinds of questions and very little of the proofs. Okay. All right, why were we interested? I want to tell you this as an anecdote. Don't try to extract a precise theorem and proof from this slide, because it's going to be too hard. These concepts are really sophisticated and took a long time to even define properly and not, but I want to tell you about this particular concept. Well, what do polynomials do? They make data robust. If you have some information, you think of it as coefficients and you evaluate, now it's resistant to change. Low degree testing can do something else robust, proofs. I mean, proofs are objects that we all work with as mathematicians. We always know that proofs are actually non-robust quantities. You look for proof on Google today, the first image that you will find will be a proof of 1 equals 2, and it's wrong in only one place. Okay. This is typically what you see as proofs. I mean, proofs are brittle objects. You change it in one location, you can prove anything you want. But low degree testing allows us to give a way of writing proofs which will be extremely robust to errors. You can detect errors easily. So this connection between data and proofs is something that's at the very essence of the theory of computer science. Proofs are that which make, what is a proof? Proof is data which makes the theorem obvious. Every theorem is either true or false, but if it's true, we can't necessarily determine the truth easily on our own. That's the hard part of being a mathematician. Once you generate the proof, you can just sort of think of it as a large piece of data which makes the theorem obvious. You can easily verify that the theorem is true once I give you this data, once I give you this proof. If you take a robust proof is something that should imply the truth of the theorem based on local tests. You should be able to look at the proof in a few places and say, yes, I believe the theorem. Can this, all evidence so far, all the examples of proofs that we've seen thus far seem to suggest that this is an impossible concept to strive for, and yet in the theory of computer science, with all these people having worked on it just to define the concept, by the way, there is this concept around called probabilistically checkable proof, or PCP, and what a PCP asks for is the following. It says, look, I want a proof of this statement, and it should have the feature that I should be able to look at it in random locations, strategically chosen, correlated locations, but I am allowed to use randomness in how to look at the proof, and if the theorem is false, I should be able to detect it. If the theorem is true, then, and you got the right proof, then I should accept it. Okay. Such objects actually do exist, and how did we get to these objects? We got to these objects by starting with the standard classical proof, making it robust using polynomials, and then the first thing we do with this proof is we do a low degree test. We say, look, did you actually specify, are you even encoding some polynomial? If you are not doing this, then I am clearly entitled to reject, because you were asked to take your proof and write it as a low degree polynomial. Then there are other things that you need to do, and I won't go into it, but this is the reason why we started looking at low degree testing. Okay. All right, so this was some motivation as to why we did this. The underlying things, statements over here, concepts are formally defined, very careful, they are actually the right notions, and there is this thing called the PCP theorem and many variations which actually tells you that you can verify proofs without, with very few queries. Okay. All right, so okay, there's a further motivations in combinatorics that comes up for why study low degree testing, but I won't talk about it right now, because see that I'm sort of already approaching the I'm closer to the end of the talk than the beginning, but not according to the number of slides I have to go. All right, so formal definition. So recall, this was what a low degree test was, and we wanted to design tests which have very small locality, while the probability with which you are rejecting things which are far from polynomials are high. When you want to look at things which are very far from polynomials, even on local views they are very far from being acceptable. That is the general goal. How do you get these kinds of things? We saw an example for linear functions and that seemed to make sense, but how do you extend it to general low degree things? And it turns out that the process of extending is actually very simple, clean and abstract, and you do not have to do very complicated things. Very simple geometry leads us to the right test. And what is the geometry? If you look at a function in n variables where n is very large, and you say it is a polynomial of degree at most d, well, it remains a polynomial of degree d even when you look at this function on a small dimensional subspace. Okay, that's affine subspaces preserve the degree, or they do not increase the degree. Okay, it's a very obvious and simple statement that I am making, right. What am I doing? I am taking any one variable and replacing it by an affine function in a few parameters, the number of parameters that it takes to capture the dimension of the subspace. Of course, these linear substitutions do not increase degree. Okay. So, for every affine subspace A, if I look at some function f of degree at most d and I look at the function restricted to that subspace, I get a new polynomial in d variables in sort of dimension of A variables, and its total degree is still at most d. Okay. So, what does it suggest? It says I do not have to look at n dimensions, I only have to look at t dimensions. But what value of t is good enough? Can I look at a function of degree 3 in over f2 restricted to 2 variables and test to see if it is a polynomial of degree 3? Okay. The answer is no, that is no good. Every function over a field of dimension of size 2 when restricted to 2 variables is a polynomial of degree 2, agrees with a polynomial of degree 2. So, there is certainly some non-triviality in the choice of what is the smallest number of dimensions I can restrict it to before this test is a good one, but that is all we have to determine. And if that number of dimensions happens to be a constant independent of the number of variables that we are starting with, then we are in business, because the number of points that we are looking at is some constant independent of the number of variables. We are only looking at points on a finite dimensional subspace. In a t dimensional subspace there are q to the t points. Okay, that is all we have to look at. So, what is the converse to this above statement? How many dimensions can I hope to look at? Turns out there is a dimensionality. The dimensionality depends only on the field size and the degree. It looks roughly like degree over field size. Okay, to within a constant factors it is really degree over the field size. And why? It is fairly obvious. Every function in one variable over fq is a polynomial of degree q minus 1. Every function in 2 variables is a polynomial of degree twice q minus 1. T variables is a polynomial of degree t times q minus 1. If t times q minus 1 is less than your testing degree d, then clearly looking at t dimensional restrictions is going to give you no information. Every function is a polynomial of degree d less than or equal to d. So, you need to make t a little bit larger than this. How much larger? It is some constant factor larger, depends on q and f and so on, but that is what it works out. So, there is this t sub qd. T sub qd is roughly d over q to within constant factors, and the natural test is to pick a random subspace of dimension exactly t sub qd, whatever is the minimum dimension for which you can actually reject every function of degree greater than d, and accept this function if on this random subspace it works out. Okay. That is the test. It works, and it works with amazingly good parameters. So, in some of the slides that are coming up, I will tell you what kinds of theorems are available. If you get nothing else from the talk, at least sort of these theorems should be fairly precise and crisp, and they should be, I mean, at least take my word for it, they are nice and strong, they are usable as a black box, and hopefully you will find other reasons to think about them. So, like I said, what does t sub qd look like? What is the smallest dimension to which you can restrict and hope to have a successful test? It is some number like d over q, between twice d over q and d over q, and that is as much as I want you to remember. So, the locality of the test that you are looking at is something like q raised to the power d over q. If d happens to be less than q, then think of this as q. If d is greater than q, then look at the ratio of the two, and that is the dimension of the space that you are looking at roughly. So, and you can actually prove that you cannot really look at less than q to the d over q points with the right constant stuck in here and hope to get any reasonable test. So, this is really the correct number. You really, if you look at too few points, you will not get any valuable test. Does not matter whether you are looking at a subspace or not. If you look at a little bit more, you have a hope, and the theorems will tell you that these are actually very good tests actually. So, how good are the tests? So, what we have now figured out what is the locality we are going to get. The L that we were seeking is going to be something like this q to the d over q. What is the epsilon that you are going to get? So, I give you a function with this differing from low degree polynomials in 1% of the points. How far away is it going to be? What kind of alpha are you going to get? So, and one of the questions that we will be asking is, does it really help to go take much larger dimensional spaces and look at functions over there? Is this beneficial? And the answer is probably yes and no. All right, so there's this one page has all the results. It took a long time to evolve to this page, but all the results have now been compressed into the 3 theorems that I will list here. So, these are the 3 theorems that you can take away, and that tells you almost everything we want to know. The first setting that we were interested in is q, the field size is constant. Think q equal to 2, q equal to 3, q equal to 5, 8, etc., etc., any prime power. And now we are going to let d also go to infinity. What kind of behavior do you expect? The locality, we cannot help it. You are going to get q to the d over q, that is the best you can hope for, and there is even a minimum number, and that is the best you can hope for. What we are able to show in these series of papers over here is really the epsilon that you get is an absolute constant independent of the dimension of the functions that you are working with, also independent of the degree that you are testing for, only depends on the field size. And so if you are looking at field size 2, there is some absolute constant that was interesting here. Even this absolute constant, I will point you to why this is an interesting theorem in a few minutes, but you can. So, the probability with which you will reject a function is proportionate to its distance from the space of degree d polynomials, and the constant of proportionality is an absolute constant depending only on the field size. This constant, by the way, is like an Ackermann function dependent on the q, but it's a constant. Okay, that is one of the theorems in this area. A second theorem that we are able to prove is in the other setting, when you are looking at d smaller than the field size. Think of d over q as a constant, d as a constant multiple of q, but less than 1. Why is this an interesting setting? This is where we get the best error correcting codes, so to speak. Recall that in this setting, the code that we are looking at has distance 1 minus this constant. So, you could be looking at anything like 1 d over q is like 1 minus delta naught or something like that. So, very, very, very close to 1, any setting that you are looking at. And now take q going off to infinity. So, d is also going to infinity with q, but the ratio is the same. In these cases, the test that you would hope for is you are looking at all of these functions, but you can hope to look at a one dimensional restriction of this function and test, I am on this one dimensional function, restriction is my function a degree d polynomial. It is actually a non-trivial thing that you could do. We are not able to analyze the one dimensional test perfectly, but we can do something slightly weaker. Look at the function restricted to 2 dimensional subspaces. So, that is q square points that I am looking at the value of the function at. But on these q square values of the point, I won't be able to, I am not going to tell you that you are actually not going to be a degree d polynomial, but I am going to tell you much stronger. If you were starting off from being 50% far from being a degree d polynomial where you started, on this 2-dimensional restriction, most of the times you are going to be 1% far. So, there is a constant relationship between the global distance and the local distance, and the constant is determined only on the gap between 1 and d over q. That is what is being stated over here in formal terms. By the way, I have this these slides, I will sort of put them on my website. You can take a look at these precise statements of the theorems and try to digest them. The statements here are very careful, my caricature might be not so. Finally, when d over q goes to 0, when the field size is larger than the degree, but actually much larger. So, think of it as 100 times larger or 1000 times larger, or in general there is some parameter and it is going off to 0, then actually the kind of robustness that you get is really nice. It is the best possible robustness you can hope for. What is the best robustness? You have some global distance. My function is 29% far from degree d polynomials overall. There is some polynomial which is agreeing with this function in 29% of the places. I look at it on a random line. What is the distance I should expect? Very close to 29%. So, the global distance and local distance should be almost equal. The best robustness you can hope for is 1, and in this setting there is a beautiful result due to Raz and Safra which says that 1 dimension again does not work too well, but 2 dimensions works very nicely. On 2-dimensional surfaces you expect to be 29% far on most 2-dimensional surfaces. That is exactly. So, the robustness you get is arbitrarily close to 1. Okay. That is the kind of theorems that we have. So, these are the 3 theorems that I think capture the entire domain. Now, I think I should take 10 minutes or something. Okay. So, in the remaining like 10 minutes or so, maybe I will tell you a little bit about the history of the first of these theorems. What was some of the more specific motivation for these questions, where did people look at it, and the kinds of analysis that lead us to this. Our analysis, by the way, is probably the most simple analysis that you could do in the setting, where it comes after a lot of more complicated analysis that you could get. So, one view of in 2-dimensional things, if the field size is 2, let me describe the test again. What will it do? I have a function of degree d. I am testing to see if a function has degree d. If I look at the function on d dimensional spaces, every function is a degree d polynomial. Okay, no good. So, I cannot look at a d dimensional space and do anything. I must look at a d plus 1 dimensional space. Okay. On a d plus 1 dimensional space, what am I going to do? I am going to look at the 2 to the d plus 1 points. That is how many we have. The domain size is 2. Sorry, I am run out of battery here. The domain size is 2, and so there are 2 to the d plus 1 points. I am going to look at this function on these 2 to the d plus 1 points and then do something. Sometimes I am going to accept, sometimes I am going to reject. There is a concrete way of looking at it, and this is the way most people in the past had been looking at it, and that concrete way was motivated by this concept called the discrete derivative. If I look at a function f, I can create a related function called f sub a, which just looks at the function at x plus a and then subtracts off the value of, sorry, that should have been x here, f of x. Okay. Why f of x plus a minus f of x? Well, this function has degree 1 less in x. Okay. This is what you would expect, and really this is what happens. Okay. Sorry, that should have been f sub x. Now, you can keep taking more and more derivatives. Okay. So, now take a derivative in direction b, a derivative in direction c, and so on, a1, a2 and so on up to a d plus 1. Take derivatives in d plus 1 directions of that function. So, take f sub a, now take derivative of f sub a in direction a2. Now, take f sub a a2, take its derivative in direction a3, etc., etc. After d plus 1 derivatives, your function should have degree 0. Sorry, your function should be the 0 function. Okay. And so, if you so this function is the 0 function, and you can try to test for it. To compute the value of this derivative at one point, you have to look at the original function at 2 to the d plus 1 points, and it turns out you are really looking at this d plus 1 dimensional subspace spanned by a1 through a d plus 1. Okay. That is really what is going on. So, this tells you what is the real test that we are doing, and this derivative view was really very key. Why? Because if you take this, let us look at the rejection probability of our test. What is the probability that this function at a random point is not 0? Okay. That can be described as a measure associated with a function. If you take a closely related measure, which is 1 minus 2 times that quantity to the power of 1 over 2 to the d, I do not know why these particular numbers, if you look at it, these numbers, now you actually get a norm on functions, and this is what is a special case of the Gowers uniformity norm on functions. And so, what this low degree testing is really analyzing is the question, so when functions have degree less than or equal to d, they have norm 1. If your function happens to have noticeably positive norm, is it noticeably close to being a degree d polynomial? That is the kind of question that one was really asking. There was a strong inverse conjecture which was probably came up in the computer science literature even more strongly than in the thing, which said that, look, if the rejection probability is approaching a half, random functions, as we pointed out earlier, over fields of size 2 would be rejected with probability half. That is the best your rejection probability can be. Then we would like to say that if your rejection probability is approaching, if your function distance is approaching 1/2, then your rejection probability should approach 1/2. This was a conjecture that was made in some of the computer science literature at least, and it was actually falsified in 2 different papers, Lovett and Mechoulam and Green and Tao, who said that, look, actually it turns out that if you took some particular values of d, and I am testing to see if a function has degree d or not, and I take the d plus 1th symmetric polynomial, elementary symmetric polynomial, it will look like a degree d polynomial on many d plus 1 dimensional subspaces, many d plus 1, constant fraction larger than 1/2. It is on like 1/2 plus 2 to the minus 7 is the easiest thing I could prove. We did prove this in one of our papers. On the other hand, it is very far, where the distance from low degree polynomials is nearly optimal, half minus some quantity which vanishes as n goes to infinity. So, this strong version of the conjecture was known to be false, but what is the best relationship that you can prove between rho of f, the probability with which this test rejects, and delta of f, the distance from these things? This is a very natural question in this setting. Till our work, there was really no very good relationship of this precise question, and then what we were able to show is okay, actually there was some explanation which said that, look, if you are taking functions which are almost as bad as random functions, this distance is approaching 50%, then they would be rejected with probability at least 4 to the minus d. This was work of Alon, Kaufman, Krivilevich, Litzen and Ron. So, it will be rejected with positive probability, but the probability goes to 0 as d goes to 0. What our lemma, the statement that I mentioned earlier, says is actually no, you are going to actually reject it with some constant, which absolute constant. I think we proved something like 1 over 1000 or some such thing in this paper, and even better, actually if your function is noticeably close to low degree polynomials, you will reject it with very high probability. But however, once this quantity becomes larger than 1 over 1000, you do not get any benefit, but you will reject it with probability at least 1 over 1000. Okay. So, this is an absolute constant relationship over here. And I can't give you much details of the proof at all, and this is all that I will try to tell you about, but here is the kind of a key question that we sort of honed down. I have a function which is reasonably far from degree d polynomials. Let us say its distance is at least 2 to the minus d. To change its value on 2 to the minus d fraction of the points in order to get a degree d polynomial. How many hyperplanes can there be? Co-dimension 1 subspaces, affine subspaces of dimension 1 less than the maximum possible. How many dimensional subspaces can there be on which this function ends up having degree at most d? Okay. This, it's a very innocuous looking question. I have a function which is very far from being a degree d polynomial. I am looking at restrictions to 1 dimension less than the whole space. How many hyperplanes can you have on which this thing is less than. When we started off, it was even not clear to us that there should be a constant fraction of the space, but that was fairly easy to prove. So the fact that there is at least one dimension, codimension 1 subspace on which your degree is greater than d is implied by the fact that I am allowed to test on subspaces of dimension 1 less or even smaller. Okay. There is a fairly simple algebraic analysis which will tell you that actually on 1 over q fraction of the subspaces. So if you are looking at q equal to 2, 1/2 of the subspaces you should actually have degree greater than d. Okay. And this actually does not even matter, just the fact that the original function had degree greater than d implied d implied this. What we really wanted to prove was not any of these quantities, but really saying that the number of subspaces on which you could end up dropping in degree to having degree less than or equal to d is at most 2 to the d. The constant outside can be like 10 or 1000 or some such thing, but not anything depending on d, anything else. 2 to the d was the absolute number we wanted, and in this case it turned out that there was a relatively simple algebraic proof. When we asked analogous question, when we looked at not degree, field size being 2 but field size being 3, immediately we could not extend this analysis. We needed Roth's theorem, for those of you who have seen that, and when you wanted to look at general q, it became Hale-Hewitt's theorem and so on. But fortunately all of these statements turned out to be sort of true in the sense that we liked it, and what we were able to say is that, look, this is the lemma that we were able to prove. The number of subspaces on which you get degree less than or equal to thing is really related to the size of the number of points that you are testing. Very strangely, this relationship comes up. I mean, there is no good reason that this should be there, but that is the statement, times some constant. This constant depends on the field size but not on the degree. So let me stop at this stage. There are other theorems and I can tell you a little bit more. These slides will say more, but no, not in this talk. So what the summary is, there is a very simple problem out there, this low degree testing problem, and it is very easy to state. It turns out to be quite useful in computational complexity, in combinatorics, but also I would suspect in other areas. I mean, it is just we have not seen real connections in other cases, and there are lots of very powerful theorems that are known, and hopefully if you look at this question or you get somehow encounters one of these questions, you will find other connections. Okay. Thank you very much.